Hi, my name is Amreish, and for this computer organization and architecture group project, I was responsible for benchmarking the storage subsystem using CrystalDiskMark version 9.0.3. And in this video, I'll demonstrate how I use the tool to extract the performance data for workload A and workload B, and walk through the analysis of those results. So as you can see here, here's my CrystalDiskMark running with an admin privileges turned on, which is required so the software can accurately access the storage controller without interference from the window protocols or Windows security protocols. And I've selected my C double drive here, and I'm keeping my default 1 GB test file size. Okay, so to configure the specific test required for this project, I go to settings and I'll go to settings again. And in this block, which can't be seen, but you can change this. You can change the block size, queue depth, and also track count for each test row based on the settings. And but so I've actually configured all of the settings already previously. And yes, so for workload A, I configured the R&D 4K row to use a 4 KIB block size, a queue depth of 32, and one thread. This creates a heavy queue random access test labeled R&D 4K Q32 T1. Okay, and for workload B, I have configured the separate row SEQ64K using a 64 KIB block size with no queue depth and one thread. And unqueued sequential test, I label SEQ64K Q1 T1. Okay, so right now I'm going to run the test for Q R&D 4K Q32 T1. So I'm just going to run it now, and it will soon show the result after it runs. For workload A, after running R&D 4K Q32T1, the results show a read speed of 336.88 megabyte per second and a write speed of 211.32 megabyte per second. These throughput figures are used to evaluate the memory bus control overhead. And by comparing this against the drive's rated sequential bandwidth, I can quantify how much performance is lost specifically due to random access. And if I change this megabytes per second to IOPS unit on the top right here, this gives the read IOPS of 82,245.61. And the reading for write IOPS is 51,592.77. These IOPS values are used to evaluate DMA versus interrupt IO handling by calculating the CPU load that interrupt-driven handling would require at this operation rate. I can demonstrate why DMA is necessary at this IO density. Okay, so right now I'm going to switch back to megabyte per second, and I'm going to run the SEQ64K Q1T1 for my workload B. For workload B, I run the SEQ64K Q1T1 test, and this produces a read speed of 502.67 megabyte per second and a write speed of 957.67 megabyte per second. Actually, these results all may vary slightly from my report because the uh, the testing of these tools all is also affected slightly by the background activity of the PC. Yeah. So this okay, and moving on, these results of the SEQ64K Q1T1 are used to evaluate a non-burst system bus latency and catch line fail buffering control limits, which I'll compare against the workload A results in the next section. And yes, so right now we're about to start our analysis and discussion. Starting with the memory bus controller, the BC901 is rated 5,000 megabyte per second sequential read. My RNDK 4K Q32T1 reads of 336.88 megabyte per second right here. It's only represents only about less than 10%, like around 8%, 7% of the rated bandwidth, and over 90% of overhead. This is because 4 kilobyte access requires the bus controller to perform a fresh handshake negotiation for every single request, unlike the sequential access, which negotiates once and streams continuously. Okay, let me change this for a while. So for DMA versus interrupt IO handling at 82,245.61 read operations per second, servicing this workload through interrupt-driven I/O would require the CPU to repeatedly suspend its current task, save state, service the request, and resume for every single operation. This is not sustainable at this volume. The controller instead uses DMA, where the CPU only provides the transfer location, size, and destination, and the DMA controller handles the rest independently through a mechanism called cycle stealing. Okay, so moving on to workload B. Interestingly, my SEQ64K Q1 sequential read result of 502.67 megabytes per second actually outperformed the R&D 4K random read result, despite using the zero Q depth. This demonstrates the non-burst system bus latency perfectly, which command queuing exists specifically to hide the latency of repeated random access handshakes. But sequential access barely incurs that overhead in the first place, since each handshake's cost is spread across a much larger 64 kilobyte block. Okay, so finally, for catch line field buffering controller limits, my sequential write results of 957.67 megabytes per second right here is well between the drive's 4,500 megabyte per second rated ceiling. This is most likely supported by the BC901's pseudo LSE write catch, which temporarily buffers incoming writes before committing them to slower than flash. Similar in concept to a cache line fill buffer in CPU memory hierarchy. Okay, so in summary, this benchmark showed that storage performance depends heavily on access pattern and I/O control strategy, and not just the raw speed of storage media. So yeah, thank you for watching.